Hello everyone. So today's topic is orthogonal trajectories. This is the topic that comes in differential equations, as all of you know. Yeah. So what exactly is an orthogonal trajectory is? Actually, first you ought to know about alpha trajectory. What's an alpha trajectory is? Basically, it's a curve. It's a curve. Suppose if I have a family of curves, guys, like suppose if I have x square plus y square is equal to c square. All of you know that this is the equation of a circle, right? Now, if I keep changing c square or r square, whatever, if I keep changing r for r is equal to 1, I'll be getting a circle with radius 1. If r is equal to 2, I'll be getting a circle with radius 4. And then for r is equal to 3, again, I'll be getting another circle with radius 9. Okay. So basically, these are all concentric circles. Or in other words, what I can say is, here R is the parameter. Varying the parameter, I'll be getting similar types of curves. Here they are basically circles. Similar types of curves with different sizes or shapes. Okay. So this would be called a family of circles. Okay. Now for this family of circles, if there is a curve or another family, if there is another family, if there is another family of curves, curve family, which touches circles at an angle, which touches, better word is which cuts, I should say, instead of touches, which cuts circles at an angle alpha, then it would be called as an alpha trajectory. Alpha trajectory. If the angle is alpha, then it would be called an alpha trajectory. If alpha is 90 degrees, then it would be called as an orthogonal trajectory. Okay. So how do I know that there is an angle alpha or 90 degrees? See, basically, guys, curves are curvy in shape, right? Now, how do I find angle between a curve and another curve that is touching is, as you all know, many of you know that at the point of intersection of this family of curves, suppose this is B and the family of curves are A. Okay. Now at the point of intersection, if I draw tangent, okay, to the family of curves and this curve that is touching, if the tangents drawn at that point to both the curves are cutting at an angle 90 degrees, then they would be called orthogonal trajectories. Orthogonal trajectories. If they are cutting at an angle alpha, some angle 45 degrees or 30 or any other angle, then they will be called alpha trajectories. Okay. If this much is clear, then orthogonal trajectories means what? They are cutting at an angle 90 degrees. The curves are cutting at an angle 90 degrees. How do I know that the curves are cutting at an angle 90 degrees is, I'll be drawing their tangents and then measuring the angle between them. But physically, every time I cannot measure the angle between both of them using a protractor or something like that. So what I will basically do is, I will consider their slopes. Okay, slopes. If they are orthogonal, what should be the product of their slopes? Obviously, you all know that the product of this slope should turn out to be -1. Or in other words, I can write m1 to be -1 by m2 or m2 to be -1 by m1 or something like that. Now, slope, there's another way to write for m, yeah, guys. For m or the slope, there's another version of writing it. What that is dy by dx. Yes or no? I also can write it as tan theta, right? Because I'm drawing the tangent there, tan theta, right? So that's how the concept of orthogonal trajectories starts, which is very simple, as all of you know. But then there's one thing which you ought to remember. There's a caution which I will tell you. So basically, an orthogonal trajectory definition goes like this. What that is a curve which cuts every family of curves, every family of curves at a right angle. A right angle is called OT, orthogonal trajectory. In short, I am writing it just to save time. How do I find it? Suppose the working rule. How do I find an orthogonal trajectory? First step will be, I'll be considering the curve, family of curves x comma y comma c, where c is the parameter, guys. Changing c, I get different family of curves. This is my equation of the family of curves. Now what I will do, I will differentiate it. Differentiate one with respect to x. I'm assuming y is a function in x, so I'm differentiating with respect to x. Now this gets transformed to x, y, y prime. You understand what this is that once I take the differential equation of one, the arbitrary constant should be eliminated. The arbitrary constant C is basically eliminated. C is eliminated. Why? Because differential equation will never have arbitrary constants. Only solutions to differential equations will have arbitrary constants. How many arbitrary constants they'll have if you ask me? How many arbitrary constants they'll have, ma'am, if you ask me? As much as the degree of the different order of the differential equation is. If it's a second order differential equation, then its solution will have two arbitrary constants. If it's a third order, the solution will have three arbitrary constants and so on. So directly, indirectly, the order of the differential equation and the arbitrary constants are directly related to each other. Okay, let's do, once I have differentiated it, next thing that I'll do is I want an orthogonal trajectory for this, na. So what I will do, replace y by, many of you know, y prime by minus 1 by y prime. Minus 1 by y prime. What's my y prime? Y prime is nothing but by dy by dx. Nothing but dy by dx, guys. Okay. So replace y prime by minus 1 by y prime. And then get the solution for it. Or in other words, I'll be writing f of x comma y comma minus 1 by y prime is equal to 0 and solve it. Solve the differential equation. That's how I'll get the orthogonal trajectory. The one that I'll resultant function or resultant equation would be an orthogonal trajectory. Okay, let's do a problem in the next this thing. Yeah, thank you.